And now the unit you've all been waiting for. Waves, dude. So here's a definition of a wave. A disturbance that carries energy through matter or through space. We are going to be spending most of our time in this presentation looking at energy that moves through matter. And we'll talk about energy that moves through space a little bit later on. But no matter which way you look at it, they're both called waves. Some waves travel by themselves, and some waves are traveling as a repeating pattern. Couple of definitions. The period of a wave is the time it takes to complete one cycle. And when I say cycles, that could be the time that it takes for 4 or 5 waves to travel, the time that it takes for 4 or 5 vibrations to occur. So when we say cycles, we're also talking about waves or vibrations, any kind of regular repeating pattern. And the unit for a period is seconds. So if I were to ask you for the period of something, you might say 4 seconds, 5 seconds, 6 seconds. Frequency is the reverse of period. It's the number of waves in a certain amount of time. And the unit for frequency is hertz. So you would respond by telling me that something has 4 hertz, 5 hertz, 6 hertz when you're talking about the frequency of a wave. So frequency can be found by taking the number of waves, the number of vibrations, and dividing that by the time. Frequency can also be determined by the inverse of the period. So we have a relationship where frequency is equal to taking 1 and dividing it by the period of a wave. And we're going to have an example of how this plays out in just a second. So let's say that a boy's going to take his son to the playground, and the boy's going to hop on a swing, and he's like, Daddy, Daddy, look at me. Son, you're doing great. Keep it up. Daddy, look at me. Look at me. Son, you're doing fine. So after a while, the dad's looking at the son, and he notices that it takes 4 seconds for his son to complete one full cycle. And a full cycle would be if you're starting right here, and you're just swinging back and forth and back. So a full cycle would be to start on this end, go all the way over, and then go all the way back. So that's a full cycle. And the question is, what's the boy's period? Well, period, the symbol for period is a capital T. And period is the time that it takes divided by how many cycles? Well, it took him 4 seconds to complete one cycle. So his period is 4 seconds. Frequency is the inverse of the period. So the frequency of the little boy is decimal 0.25 hertz. Let's look at another example. Julie loves to surf. So she gets out there on her surfboard, gets out in the deep water, and she's just waiting. Dude, I'm so tired of waiting. So while she's waiting, she decides to count. Luckily, she has her diver's watch on. She notices that 2 waves pass underneath her surfboard in every 10 seconds. So again, let's look at that period. Okay, period would be the time divided by the number of waves, the number of cycles. So pretty straightforward here. We take the time, which was 10 seconds, and we divide that by 2 because that was the number of waves she counted. So her period is 5 seconds. The frequency would be 1 over the period. So that would give us 1 over 5, or 0.2 hertz. Another way of looking at the frequency could have been to look at the number of cycles and divide it by the time. And in this case, you would take the number of cycles, which was 2, and divide it by the time, which was 10. You still get 0.2 hertz. So these are a couple of ways to be able to calculate the period of a wave and the frequency of a wave. If you haven't noticed by now, definitions or vocabulary words are bold print, so definitely pay attention to those definitions. The movement of a wave is definitely influenced by the material through which it travels, and that material through which it travels we call the medium. The medium is the type of matter, whether it's a solid, liquid, or gas, and we know that sound has an average speed of about 340 meters per second in air, which is a gas. But in water, the sound energy travels about 4 times faster because the particles or the molecules are closer together. And the sound travels even faster through a solid material, such as iron or brick. The closer the particles are, the more quickly sound travels. We can look at this relationship in this formula where V stands for the wave speed equals lambda. That is the Greek symbol for wavelength. So it's pronounced lambda times the frequency, which we've spoken about before. So the speed of a wave is its velocity is equal to the wavelength, or lambda, times the frequency. So just to give an example of how the medium affects the velocity, if you think about somebody talking to you with a very high-pitched voice, that's one frequency, and somebody talking with a low-pitched voice, that's another frequency, and if they were both talking at the same time, their sounds would arrive at your ears at the same time. So the frequency at which they speak doesn't really influence how fast the wave travels, especially a sound wave. It's more the medium. The fact that it's traveling through air is what makes a difference as the speed. So let's look at another example. So here we have Lounge Lizard Larry. He's so proud of his new system that he just installed in his car. So he's got all the people walking over, come on man, come check out my sound system. So it produces this very high-pitched 16,000 hertz sound. And we know that the speed of sound is about 340 meters per second. So we can actually use these two pieces of information to find out the wavelength. So let's look at the formula. Velocity is equal to lambda times frequency. So we know that the velocity is 340 meters per second. We don't know the wavelength, but we know the frequency is 16,000 hertz. So if we want to solve for just the wavelength, and we find that lambda is equal to and since it's a distance, wavelength is a distance, it's measured in meters. So it may not make a whole lot of sense. If you were to convert this into centimeters, that would basically be 2.2 centimeters. So that's about an inch. So what we're saying here is that the wavelength of this wave is about 1 inch from one place to the other. And we're going to talk about the parts of a wave pretty soon here. There are basically two types of waves, mechanical waves and electromagnetic waves. We are not going to focus on electromagnetic for this part of the unit. We'll get to those a little bit later. We're going to focus on mechanical waves. And there are two types of mechanical waves, longitudinal waves and transverse. What both of these waves have in common is that they both require a medium to be able to transfer energy. Longitudinal waves and transverse waves are types of mechanical waves, and all mechanical waves require a medium to transfer energy. So let's start first with the longitudinal wave. Here's an example. You can see the spring. As the spring is pushed on the left side, it the pulse travels from one end of the springs to the other. And so notice how sometimes the spring is compressed. Right there it's compressed, and then it relaxes and it's thinned out. When it's compressed, we call it a compression. So that's what we have right here, a compression. And the particles are pushed together or squeezed together. When it's relaxed, we call that a rarefaction, when the particles are spread out, they're less dense. The wavelength is from compression to compression or from rarefaction to rarefaction. The amplitude is thought of to being how thick the compression is. All in all, a longitudinal wave is a wave in which the energy moves in the same direction that the particles move. So if you'll pay attention, the energy and the vibrations are moving in the same direction. They're both moving kind of, in a sense, parallel to each other, but they're not parallel. So the pulse goes that way and the particles vibrate that way. An example of a longitudinal wave is a sound wave. So every time your vocal cords vibrate, they create a longitudinal wave. As you observe this animation, you can see this bar over here kind of pushing the waves, and you can see that they squeeze the particles together, and the energy or that pulse travels the length of this tube. But if you pay attention to the red dots, like for the example the one right here, you'll see that it basically just kind of vibrates back and forth. But it vibrates parallel to the energy's movement. So the pulse goes all the way through, but the particles only vibrate in a small area. Our second type of mechanical wave is a transverse wave. And here we have the energy moves perpendicular to the wave's direction. And you'll see this in an animation in just a moment. Right now we'll concentrate on the different parts of a transverse wave. So the amplitude, as you can see right here, would be, if this was the original resting position, the amplitude is basically from where the wave was before it was disturbed, the medium was disturbed, to the top. You can also have an amplitude that would be in this area. So amplitude is not the whole wave. It's definitely not the whole wave. It's only from the resting position to where the displacement occurs. An example of a transverse wave would be like a water wave. If you were to drop a rock, you would create peaks and you would create valleys. And those peaks are called crests and the valleys are called troughs. So here we look at our animation of a transverse wave, and if you isolate one particular dot and follow that one dot, you see that the dot vibrates up and down in a the dot vibrates up and down in a vertical motion, so which is perpendicular to the way that the wave moves. The wave seems to move in that direction. So if you follow the peak, it's kind of going that way. But the particles are vibrating up and down, so perpendicular. So a transverse wave is when the vibrations are perpendicular to the motion of the energy.